Gravity is an architect with a very strict set of rules. It wants to pull everything together, to crush matter down into the smallest possible space. But there is a war happening inside every bright object out there in the dark. A brutal, endless war between the crushing weight of gravity pulling inward and the furious energy of a continuous nuclear explosion pushing outward. We call this delicate balance a star. But there is a breaking point, a physical ceiling to how big that explosion can get. If you build a skyscraper too tall on Earth, the concrete and steel at the bottom will simply shatter under the sheer weight of the floors above. The structure destroys itself. The universe works exactly the same way. For almost 100 years, the brightest minds on our planet believed they had found the absolute maximum size a star could ever reach. They ran the numbers. They mapped the equations. They proved that if a star gathered too much mass, the nuclear fire in its belly would become so incredibly intense that the outward pressure of the light itself would blow the star apart. The radiation would literally peel the outer layers off and throw them into the freezing void. This was a mathematical wall, a cosmic speed limit, and we thought we knew exactly where it was. But out in the terrifying expanse of deep space, hidden behind thick, twisting rivers of cosmic dust and violent radiation, something is breaking that rule. Something is mocking the math. Astronomers have found an anomaly, a monstrous, burning sphere of plasma so violently huge that it makes our own sun look like a microscopic speck of dust floating next to a roaring bonfire. We are talking about an object so impossibly heavy and bloated that the light fighting to escape its core takes hundreds of thousands of years just to reach the surface. It is a giant that burns with the blinding fury of millions of suns, radiating a heat so extreme it should have destroyed itself the moment it was born. By every single law of physics we understand, this colossal object should not be sitting there. The sheer, overwhelming force of its own internal light should have ripped it to shreds long before we ever pointed our telescopes at it. It should be a scattered cloud of dead ash. But it is not dead. It is burning, a glaring, aggressive anomaly staring back at us from the void, forcing us to realize a very uncomfortable truth. When you find a monster that ignores the laws of nature, you have to admit that your laws were wrong. We are just trying to draw maps of a deep, dark ocean while standing in a tiny, safe puddle. The discovery of this impossible giant is a glowing red warning sign out in the dark, telling us that the universe is much wilder, much heavier, and far more dangerous than we ever dared to imagine. To understand the monster we have found hidden in the deep dark, we first have to unlearn everything our human brains tell us about how the physical world works. We are creatures of comfort. We love the illusion of stability. We trust the solid ground beneath our feet, and we trust that the sun will rise every single morning, calm and reliable. Because of this, our intuition plays a trick on us. We look at stars as if they are permanent, peaceful objects, like glowing streetlights bolted to the ceiling of the universe. But a star is not a calm object. A star is an ongoing, catastrophic explosion that is desperately trying to contain itself. It is a raging war zone, and to understand the absolute breaking point of this war, we have to talk about the two invisible forces fighting it. The first force is gravity. Gravity is the ultimate dictator of the cosmos. It wants to pull everything inward. If you gather enough hydrogen gas floating out in the freezing emptiness of space, gravity will start pulling it all together. As more and more gas piles up, the weight of it becomes crushing. Imagine millions of billions of tons of invisible weight pressing down from all sides, squeezing that gas tighter and tighter into a sphere. As it squeezes, the core gets hotter. The pressure builds. It becomes a pressure cooker with no safety valve. Eventually, the pressure in the very center of that sphere becomes so unimaginably violent that the atoms themselves are crushed into each other. They fuse together, and when they fuse, they release a tremendous, terrifying amount of nuclear energy. A nuclear fire is ignited. This is the birth of a star. Now, this nuclear fire creates the second force in our cosmic war. The outward push, the explosion pushing back against the crushing weight. For the entirety of a star's life, these two forces are locked in a brutal stalemate. Gravity pushes in, the nuclear fire pushes out. As long as these two forces remain perfectly balanced, the star survives. It becomes that steady, reliable, glowing orb we see in the sky. But what happens if you add more fuel to the fire? What happens if gravity pulls in even more mass? Our human intuition tells us that bigger is always stronger. If you want to build a stronger bridge, you use more steel. If you want a more powerful engine, you build a bigger machine. We assume that if a star gathers more gas and becomes heavier, it simply becomes a stronger, more powerful star. But the universe does not care about human logic. In the cold mechanics of space, building a bigger star does not make it stronger. It makes it incredibly fragile. To understand why, we need to talk about something that sounds almost like magic, but is actually one of the most fundamental rules of physics. We need to talk about the physical weight of light. When you stand outside on a sunny day, you feel the heat of the sun on your skin. But what you do not feel is the light physically pushing you backwards. That is because here on Earth, the light from our sun is incredibly weak. But light is not just a visual thing. Light is made of particles called photons. And even though photons do not have mass in the way a rock or a piece of metal does, they carry momentum. When they hit an object, they push it. Imagine walking outside into a hurricane. You feel the wind slamming into your chest, pushing you back. Now, replace the wind with pure, blinding light. Deep inside the core of a star, the light is so incredibly intense and so overwhelmingly bright that it acts exactly like a physical hurricane. The sheer force of the glowing radiation pushes outward against the crushing weight of gravity. Scientists call this radiation pressure. For a normal star, like our sun, this radiation pressure is just a gentle breeze helping to hold up the roof. But when you start building a giant star, the rules completely change. As a star gets heavier, its core is forced to burn its fuel much, much faster just to keep from collapsing under its own massive weight. And here is the trap. The temperature does not just go up a little bit, it skyrockets exponentially. If you double the weight of a star, its core does not just burn twice as bright. It burns thousands of times brighter. The heavier the star gets, the more violent the nuclear engine becomes. The gentle breeze of radiation pressure turns into a raging, chaotic storm of physical force. The light itself becomes a weapon. In the early 20th century, astronomers began to realize that this created a very serious mathematical problem, a theoretical ceiling. They calculated that if a star kept gathering mass, growing larger and larger, the nuclear fire in its core would eventually become so insanely hot that the outward hurricane of light would actually overpower gravity. Think of it like pushing the human body past its absolute physical breaking point. Imagine a runner pushing themselves so fast and so hard that their lungs physically cannot draw in enough oxygen to keep the machine running, or a weightlifter trying to hoist a mass so terrifyingly heavy that the bones simply splinter and fail under the load. At a certain point, the structure cannot support its own ambition. It destroys itself from the inside. The math told us exactly where this breaking point was. An astronomer named Arthur Eddington mapped out this cosmic boundary. He proved that if a star grew to be about 150 times the weight of our own sun, the radiation pressure would become unstoppable. The outward blast of pure light would be so aggressive that gravity would lose its grip entirely. If a star tried to grow past this limit, the light would literally blow the star apart. The outer layers of the star would be ripped violently away and thrown out into the dark void. The star would peel itself like an onion until it was light enough for gravity to take control again. This became known as the Eddington Limit. It was a beautiful, elegant, and brutal law of nature. It told us that stars could not just grow forever. There was a strict, unforgiving cap on the size of things in our universe, 150 times the weight of our sun. That was the wall. That was the ceiling. It was a rule written into the very fabric of physics. If you cross this line, you die. For decades, we felt comfortable with this rule. It made sense. We looked at the night sky, catalogued the giant stars, and found that they all obeyed the law. Even the biggest, brightest, most terrifying supergiants we could find always stopped growing right before they hit that invisible wall. Our textbooks were printed. The science was settled. We understood the mechanics of the cosmic machine. We knew exactly how big a fire could get before it blew out its own walls. But the universe has a very dark sense of humor. Just when you think you understand the rules of the game, the universe changes the board completely. Because out there, floating quietly in a neighboring galaxy, spinning in a chaotic cloud of brilliant gas and heavy dust, is an object that should not exist. A star that somehow swallowed the Eddington Limit and kept on growing. We are talking about a physical impossibility, a living contradiction burning in the dark. A cosmic giant so completely saturated with raw energy that it is forcing us to tear out the pages of our own physics books and ask ourselves a very dangerous question. What else are we completely wrong about? If you seek the truth in the dark, subscribe and join us on this journey. To find this impossible anomaly, we have to leave the safety of our own galaxy. We have to travel across an unimaginably vast, freezing ocean of completely empty space. Imagine stepping outside your house on a pitch-black night, leaving the glowing lights of your city far behind, and walking out into a desert that never ends. That is what it feels like to leave the Milky Way. You are surrounded by a suffocating silence, an abyss of nothingness that stretches on for millions of years. But if you look out into that dark ocean, you will eventually see an island, a small, chaotic companion to our own galaxy, floating roughly 160,000 light-years away. Astronomers call it the Large Magellanic Cloud. At first glance, it just looks like a faint smudge of light, but hidden inside that smudge is a region of space so violent and so extreme that it has terrified and fascinated scientists for generations. It is a sprawling, twisted factory of cosmic creation known as the Tarantula Nebula. To call the Tarantula Nebula a cloud of gas is a massive understatement. It is a roaring, turbulent storm of heavy dust, blinding radiation, and raw stellar material. It is a place where gravity is aggressively crushing hydrogen into new stars at a rate that we simply do not see anywhere else in our local cosmic neighborhood. To give you a sense of the sheer, terrifying scale of this nebula, think about the famous Orion Nebula, which you can sometimes see from Earth with your naked eye. Orion is relatively close to us, and it is a respectable nursery for baby stars. But if you took the Tarantula Nebula and moved it to where Orion is, it would not just be a pretty smudge in the night sky. It would cover a massive portion of the heavens. It would shine so intensely that it would cast hard, sharp shadows on the ground here on Earth in the middle of the night. That is the kind of environment we are dealing with. A hostile, supercharged forge. And deep inside, the very center of this glowing storm, wrapped in thick blankets of gas and dust, sits a knot of light that is so incredibly bright, it is almost blinding to our instruments. For a very long time, we did not know what we were looking at. When astronomers first pointed early telescopes at this blazing knot of light back in the 1950s and 1960s, the technology was primitive. The lenses were thick, and looking through Earth's atmosphere was like trying to look at a distant streetlight from the bottom of a murky, moving swimming pool. Everything was distorted. Everything was blurry. Looking at the data, the early astronomers made a logical assumption. They assumed that this incredibly bright region was just a very dense neighborhood of normal, average stars, all packed closely together. Just a busy, cosmic city center. But as the decades passed, our technology evolved. We built bigger mirrors. We launched the Hubble Space Telescope into orbit, placing it high above the distorting blur of our atmosphere. We built the Very Large Telescope, a massive array of mirrors sitting in the bone-dry, high-altitude deserts of Chile, operated by the European Southern Observatory. With these new, highly sensitive artificial eyes, we stared back into the heart of the Tarantula Nebula. We gathered the light, particle by particle, over hundreds of hours of agonizingly patient observation. We slowly peeled back the blur. We resolved the image. And what we saw sitting in the center of that light completely shattered our expectations. It was not a calm, sprawling city of average stars. It was a cluster of absolute monsters, a tight, aggressive gang of the most massive, violently burning objects ever recorded. Astronomers cataloged this specific core region under a cold, technical name, R136. Even among this cluster of giants, there was one point of light that dominated all the rest. One specific object that was practically screaming at our sensors. It was the undisputed king of this violent neighborhood. They named it R13601. When astronomers finally managed to isolate the light coming from this single object, they ran the numbers to calculate its weight. They expected it to be heavy. They expected it to push right up against that famous, unbreakable mathematical wall we talked about, the Eddington Limit. They fully expected it to weigh somewhere near 150 times the mass of our sun. The computers processed the light, the equations were solved, and the final number printed out on the screens in the dark control rooms left the scientists in absolute, stunned silence. The numbers said that this single, solitary star weighed approximately 260 times the mass of our sun. Some recent estimates, depending on how you read the incredibly complex data coming from the telescopes, suggest that when this star was first born, it might have weighed over 300 times the mass of our sun. Let those numbers sink in for a moment. Let them crush your sense of scale. We throw the word mass around a lot, but what does it actually mean in the dark void of space? Mass is not just physical size. Mass is authority. Mass is the gravitational power to command the universe around you. Think about our sun. Our sun is a colossal, heavy anchor. It is so unimaginably massive that its gravity reaches out across billions of kilometers of empty space to hold massive planets like Jupiter and Saturn on a tight leash. It controls asteroid belts. It dictates the orbit of comets in the freezing outer edges of the system. Our sun is the undisputed master of our tiny bubble in the universe. Now, imagine taking the sheer, crushing weight of our sun and multiplying it by 260. The amount of raw material crammed into this one single object is so absurd that the human brain simply cannot visualize it. If you were to take the Earth and drop it into a star like this, it would be like tossing a single grain of fine sand into a raging volcano. The Earth would not just melt, it would be instantly unwritten from reality. But the terrifying weight of this monster is only the beginning of the nightmare. Because a star this heavy cannot burn slowly. Remember the war between gravity and light. To keep a body this heavy from collapsing under its own apocalyptic weight, the nuclear fire burning inside its core has to work at a frantic, terrifying pace. It is burning its fuel so aggressively that it produces an amount of energy that defies all human logic. R136A1 is not just millions of times brighter than our sun. It is over 6 million times brighter. Let us try to translate that into something you can feel. Imagine a single, incredibly bright stadium floodlight shining directly into your eyes. Now, imagine taking every single light bulb, every single headlight, and every single neon sign on the entire planet Earth, and turning them all on at the exact same moment. The difference between those two things does not even come close to the difference between our sun and this cosmic giant. If you were to somehow remove our sun and replace it with this monster, the consequences would be instantaneous and absolute. The heat would not just burn the Earth. The sheer physical pressure of the light radiating from the star would hit our planet like a solid wall of force. It would instantly boil the oceans away into space. It would strip away the atmosphere in a fraction of a second. The rocky crust of the Earth would melt into glass and then evaporate into a cloud of scattered atoms. Even planets orbiting far out in the dark, freezing edges of our solar system, like Neptune or Pluto, would be scorched and stripped down to their bare, rocky cores by the overwhelming blast of radiation. Because of this violent energy output, the surface of this star is a place of unimaginable extremes. When you look at a fire here on Earth, you know that the red flames are cool, the yellow flames are hotter, and the blue flames at the very base of a blowtorch are the hottest of all. Stars work the exact same way. Our sun burns with a relatively calm, yellow-white heat. The surface of our sun is roughly 5,500 degrees Celsius. That is hot enough to melt any metal we know. But our 136A1 burns pure, screaming blue. The surface temperature of this giant is estimated to be almost 50,000 degrees Celsius. It is radiating so much ultraviolet energy that if you could somehow survive looking directly at it, the invisible light alone would physically destroy the cells in your eyes before your brain even registered the pain. But this extreme existence comes with a terrible price. A star cannot burn this violently without consequences. The monster is slowly bleeding to death. Because the outward blast of light is so incredibly powerful, the gravity of the star is actually struggling to hold on to its own outer layers. The light is literally shoving the star's skin away into deep space. Astronomers call this a stellar wind. But the word wind is a terrible, gentle metaphor for what is actually happening. This is not a breeze. This is a hurricane of radioactive plasma blowing outward at millions of kilometers per hour. The radiation pressure is so intense that the star is forcefully ejecting its own body mass out into the Tarantula Nebula. It is shedding weight at a rate that is difficult to comprehend. Every single second, millions upon millions of tons of superheated gas are ripped away from the star and thrown into the dark. It is losing the equivalent weight of an entire Earth every few weeks. It is a star that is violently consuming itself just to stay alive for one more day. When astronomers first realized the true scale of what they were looking at, panic set in. This object was a direct insult to the laws of physics they had spent their entire lives studying. It broke the Eddington Limit. It shattered the cosmic speed limit. It was an impossibility staring them right in the face. So, they did what any good scientist would do when faced with a terrifying anomaly. They tried to find a way out. They tried to prove that their own data was wrong. There was one very obvious, very desperate hope. In the chaotic environment of deep space, stars very rarely like to be alone. They often form in pairs, locked together in a tight gravitational dance, circling each other in the dark. We call these binary systems. Sometimes there are even 3 or 4 stars all orbiting a shared center of gravity. The scientists prayed that our 136A1 was not a single giant monster. They hoped that the blurry dot of light they were looking at was actually 2 smaller stars orbiting so closely together that our telescopes could not tell them apart. If it was a binary system, if it was just 2 normal stars that weighed maybe 130 times the mass of the Sun each, then the crisis would be averted. The laws of physics would be safe. The Eddington Limit would remain unbroken. It was the perfect escape route. So, they turned the most advanced scientific instruments in human history back toward the Large Magellanic Cloud. They used incredibly complex machines called spectrographs, which take the light from a star and break it apart into a rainbow barcode. By studying this barcode, astronomers can see the chemical fingerprints of the star, and more importantly, they can see exactly how the star is moving. If there were 2 stars locked in a tight orbit, the spinning motion would leave a very clear, very obvious wobbling pattern in the light. One star would be moving toward us while the other moved away, creating a signature that is impossible to hide from a modern spectrograph. The astronomers gathered the data. They filtered out the noise. They stared at the barcodes of light, desperate to see the comforting wobble of a binary system. But the light did not wobble. The barcode was flat. The signal was clear. There was no hidden partner. There was no secret companion. The data was cold, hard, and terrifyingly precise. All of that mass, all 260 times the weight of our Sun, was packed into one single, unbroken, impossibly huge sphere of boiling plasma. The escape route was slammed shut. The scientists were trapped in a room with a monster that should not exist. They had confirmed the physical measurements. They had confirmed the temperature. They had confirmed the blinding luminosity. But none of that answered the fundamental, agonizing question that was keeping astrophysicists awake in the middle of the night. If the laws of physics clearly state that a star this massive should instantly blow itself apart from the sheer force of its own internal light, how does a physical impossibility come to exist? This is the question that echoes through the halls of observatories, keeping scientists staring at their computer screens long into the quiet, dark hours of the night. You cannot just ignore an object that weighs 260 times the mass of our Sun. You cannot brush it under the rug. It demands an explanation. But when astrophysicists tried to run the tape backward, when they used the most powerful supercomputers on Earth to simulate how this monster could have possibly been born, the computers basically threw their hands up in defeat. Every simulation ended in failure. Every mathematical model ended with the star destroying itself before it could ever reach that colossal size. To understand the sheer frustration of this paradox, we have to look at how a star is actually built. We have to look at the construction site. Stars do not just pop into existence out of nowhere. They are grown. They are built from the dust and gas floating in deep space, in places like the Tarantula Nebula. Imagine a massive, freezing cold cloud of hydrogen gas. In the center of that cloud, gravity starts a slow, relentless gathering process. It begins to pull the gas inward. Astronomers call this process accretion. Think of it like building a snowball. You start with a small handful of snow, and you roll it along the ground. As it rolls, its own weight and sticky surface pull in more snow. It gets heavier. Because it is heavier, it pulls in even more snow, even faster. This is exactly how a young star gathers mass. The heavier the young star gets, the stronger its gravitational pull becomes, and the faster it violently drags the surrounding cloud of gas down onto its surface. For a normal star like our Sun, this process takes millions of years. It is relatively peaceful. The gas falls inward, the core gets hot, the nuclear fire ignites, and the star settles into a long, quiet life. But when you try to build a monster, the construction process turns into a war zone. Remember that as a star gets heavier, the nuclear fire in its core burns exponentially brighter. The light becomes a physical, outward-pushing force. Now, put yourself in the shoes of a scientist trying to mathematically model the birth of a supergiant star. You start the simulation. The young star is sitting in the center of its dark cloud. It weighs 10 times the mass of our Sun. It is pulling in gas, growing heavier. Now it weighs 30 times the mass of our Sun. The core is getting incredibly hot. The light pushing outward is becoming aggressive. Now it weighs 60 times the mass of our Sun. The radiation pressure is so intense that the light is actually fighting back against the incoming gas. Imagine trying to build a sandcastle, but someone has placed an incredibly powerful industrial fan deep inside the center of your sand pile, pointing outward. Every time you try to throw a new bucket of sand onto the pile, the violent wind from the fan simply blows the sand right back into your face. The sand never even touches the castle. This is the exact wall that astronomers hit when they try to explain R136A1. When a growing star reaches about 100 times the weight of our Sun, the light blasting out of its core becomes an almost solid physical shield. The radiation is so blindingly intense that it vaporizes the surrounding cloud of gas and physically shoves it away into deep space. Gravity is desperately trying to pull more fuel inward, but the light is blasting it away before it can even reach the surface of the star. The feeding process is choked off. The star effectively starves itself by being too bright. By the time the star reaches the famous Eddington Limit, 150 times the mass of our Sun, the outward blast of light is absolute. The door is slammed completely shut. It is mathematically, physically, and logically impossible for a single drop of new gas to fall onto that star. The radiation pressure creates a dead zone around the giant, a bubble of force that nothing can penetrate. So, If the door is completely shut at 150, how in the world did this thing reach 260? If it could not gather that mass from the surrounding cloud, where did the extra weight come from? This total breakdown in our understanding of physics forced scientists into a dark corner. When the elegant, simple answers fail, you have to start looking at violent, chaotic alternatives. If the star did not grow slowly and peacefully by gathering dust, maybe it was forged in a catastrophe. This brings us to the leading theory, a theory that paints a picture of a universe so hostile and chaotic that it challenges our very definition of nature. The stellar merger theory, or, as it is known in simpler terms, a cosmic car crash. To understand this nightmare scenario, we have to zoom back out and look at the neighborhood where this monster lives. Our 136 is not a quiet suburb. It is the most crowded, aggressive, tightly packed cluster of giant stars we have ever seen. Imagine putting 1 million people into a single, empty swimming pool and telling them all to run around at top speed. It would be pure, unadulterated chaos. People would collide. People would be dragged along by the crowd. That is what the gravity is doing in this star cluster. There are hundreds of incredibly heavy stars packed tightly together in the dark, all ripping and tearing at each other with their gravitational fields. In a chaotic environment like this, stable orbits are a myth. The invisible threads of gravity are constantly pulling, stretching, and snapping. Now, imagine that somewhere in this violent crowd, two massive stars were born together. This is very common in the universe. Two stars, locked in a tight, spinning dance, orbiting around a shared center point. Let us say each of these stars weighs about 130 times the mass of our Sun. Individually, these stars are legal. They obey the laws of physics. They sit safely just underneath the Eddington Limit ceiling. They are heavy, they are burning bright blue, but they are relatively stable. But they are not orbiting in a clean, empty vacuum. The Tarantula Nebula is choked with thick, heavy gas and dust. As these two massive stars spin around each other, they have to drag their massive bodies through this thick cloud. Imagine trying to run a race while submerged in chest-deep water. The water creates drag. It slows you down. It drains your energy. The exact same thing happens to the stars. The friction from the surrounding gas slowly, relentlessly bleeds energy away from their orbit, and as they lose energy, they begin to slow down. When objects in orbit slow down, they fall inward. Over the course of tens of thousands of years, a blink of an eye in cosmic time, the two heavy stars begin a slow, terrifying death spiral. The distance between them shrinks. The gravitational pull between their two massive bodies becomes overwhelming, twisting them into egg-like shapes. Finally, the gap closes entirely. But this is not a sudden, shattering explosion like two rocks hitting each other. Stars do not have solid surfaces. They are spheres of boiling gas. When they finally touch, it is an agonizingly slow, incredibly violent merging of two oceans of fire. The outer atmospheres of the two stars bleed into each other first. A searing hot bridge of plasma connects the two giants in the dark. They spin faster and faster, spiraling and toward each other, ripping massive sheets of burning gas off of each other's surfaces. The magnetic fields of the two stars tangle together, snapping and releasing shock waves of radiation that would sterilize a solar system in a matter of seconds. Deep inside the twisting, chaotic cloud of their combined atmospheres, the two heavy, dense cores finally meet. Millions of billions of tons of superheated material slam together. The two nuclear engines fuse into one single, terrifyingly large furnace. In that blinding, cataclysmic moment, the monster is born. The two stars, weighing 130 times the mass of the Sun each, combine to create a single, solitary object weighing 260 times the mass of the Sun. The sudden addition of all that new fuel into a single core causes the nuclear fire to instantly skyrocket. The new star flares up with a blinding, terrifying fury, blasting away the remaining dust and gas, announcing its violent birth to the entire galaxy. It is a brilliant, terrifying theory. It explains exactly how an object can bypass the rules of normal star formation. It did not break the wall by growing through it. It smashed to fully formed pieces together on the other side of the wall. It makes sense. It fits the violent nature of the star cluster. But there is a massive, glaring problem with the cosmic car crash theory. A problem that brings us right back to the very first physical limit we talked about. Merging two stars together does not make the laws of physics simply disappear. Yes, the collision would create a single, impossibly heavy object, but the second that new object forms, it is still subject to the merciless rules of gravity and light. When those two massive cores slammed together and ignited into a single, combined nuclear fire, the resulting explosion of light should have been so violently powerful that it instantly blew the newly formed star completely apart. Remember, the entire reason the Eddington Limit exists is because an object that heavy cannot hold itself together against the hurricane of its own radiation. Just because it formed in a car crash does not mean it gets a free pass from gravity. The sheer force of that merged, supercharged nuclear engine should have acted like a bomb. It should have immediately ripped the star to shreds, scattering its guts across the nebula in a spectacular, short-lived fireworks display. It should have corrected the anomaly the second it happened, and yet, we look through our telescopes across the vast dark ocean of space, and we do not see an explosion. We do not see a scattered cloud of dead, expanding debris. We see a star. We see a solid, cohesive, burning sphere of plasma holding itself together. It is sitting there, burning steadily, completely ignoring the fundamental forces that should be tearing it limb from limb. This is the barrier. This is the wall that human intelligence is currently slamming its head against. We have mapped the equations. We understand how gravity pulls. We understand exactly how light pushes. We know the math of stellar collisions, and every single calculation tells us that this star should be dead. It is as if we are watching an airplane fly without wings, or a boulder roll up a steep hill completely on its own. It is a fundamental violation of the mechanical universe we thought we understood so well. Some scientists believe that the star is desperately fighting a losing battle. They theorize that the monster is not actually stable at all, but rather hanging by the thinnest, most fragile physical thread imaginable. They propose that the star is pulsating, shaking violently in the dark. Imagine an engine that has been pushed so far past the red line that it is literally vibrating itself out of its mounts. The theory suggests that the outward pressure of the light pushes the outer layers of the star away, making the star swell up to an enormous size. As it swells, the pressure inside drops just a tiny bit. The light weakens just enough for gravity to grab hold again, violently pulling those outer layers back down. The gas crashes back onto the core, reigniting the extreme pressure, which creates another massive blast of light, blowing the layers back out again. Inward, outward, inward, outward. A heavy, agonizing, violent heartbeat in the dark. If this is true, the star is not sitting peacefully. It is actively fighting for its life every single second, violently expanding and contracting, throwing off massive oceans of its own mass with every single breath. It is a chaotic, temporary state of extreme physical distress. But even this theory feels like a bandage placed over a massive, bleeding wound in our understanding of physics. It feels like an excuse. The terrifying truth that we must confront is that our models are simply incomplete. Our understanding of how matter and energy interact at the absolute extreme edges of reality is fundamentally flawed. We are like children trying to understand the inner workings of a supercomputer by looking at it through a dirty window. We can see the lights blinking. We can hear the hum of the fans. We can make guesses about what is happening inside the box, but we do not have the blueprints. R136A1 is a glitch in the matrix. It is a heavy, blinding reminder that the universe does not exist to make sense to the human brain. The cosmos is not a neat, orderly clockwork machine governed by simple rules that we can write down on a chalkboard. It is a wild, untamed, and infinitely complex system, and hidden within the crushing pressures and blinding light of these extreme environments, there are entirely new laws of physics waiting to be discovered, laws that govern the behavior of reality in ways we cannot even begin to visualize. If a star can break the absolute limit of mass and hold itself together in the dark, what other fundamental rules are quietly being broken out there in the abyss? What other invisible barriers have we constructed in our own minds, completely unaware of the terrifying truth hiding just beyond the reach of our telescopes? The discovery of this impossible giant does not just challenge our understanding of how stars are born, it forces us to confront a much darker, much more profound question about the very nature of space, time, and the inevitable, catastrophic fate of the things that burn the brightest. When a fundamental law of physics is broken, the consequences do not just stay neatly confined to one tiny corner of the universe, they ripple outward. They infect everything else we thought we knew. If a star can grow to 260 times the weight of our Sun, completely ignoring the absolute limits of nature, we are forced to ask what happens when that monster finally runs out of fuel. Because a star that breaks the rules while it is alive is absolutely going to break the rules when it dies. To understand the terrifying fate of this giant, we need to look at how a normal star meets its end. When a star like our Sun finally burns through all its fuel, it dies a relatively quiet death. It slowly sheds its outer layers, leaving behind a glowing, cooling ember. It fades away into the dark like a campfire turning to cold ash. If a star is a bit heavier, say 10 or 20 times the mass of our Sun, its death is much more violent. When the nuclear fire in its core eventually runs out, the outward push of light disappears. Gravity instantly wins the war. The entire weight of the star crashes inward, crushing the core so violently that it rebounds in a massive explosion called a supernova. What is left behind is usually a dense, dead cinder or a black hole, a permanent, silent tombstone marking where a star used to be. But R136A1 is not a normal star. It is a mathematical nightmare, and because it is so impossibly heavy, its death will not be a normal explosion. It will be an event of such absolute, pure annihilation that it forces us to question the very fabric of reality. Scientists have a name for what they believe will happen to this supergiant. They call it a pair-instability supernova. But that is just a clean, academic term for the total erasure of a physical object. To understand how this works, we have to go back deep into the core of the monster, where the temperature is pushing toward numbers that human brains simply cannot process. We are talking about billions of degrees. At these extreme, incomprehensible temperatures, the physics of the universe stop acting normally. Remember the hurricane of light, the violent radiation pressure that pushes outward and keeps the heavy star from collapsing. Well, as the core gets hotter and hotter, the light itself begins to change. The energy becomes so insanely intense that the particles of light, the photons, actually shatter. They literally transform. Through a bizarre quirk of quantum mechanics, the pure energy of the light spontaneously transforms into physical matter. It turns into pairs of particles. Think about what that actually means. The light, the very thing that is acting as the structural pillar holding up the entire crushing weight of the star, suddenly stops being light. It turns into mass. Imagine you are standing inside a massive, heavy stone cathedral. The incredibly heavy roof is held up by thick, solid steel pillars. Now, imagine if, in a fraction of a second, every single steel pillar inside that building instantly turned into thin air. There is no warning. There is no slow bending or groaning of metal. The support structure simply ceases to exist. That is exactly what happens inside this monster star. The outward pressure simply vanishes. Without the light pushing back, the absolute, terrifying gravity of a star weighing over 200 times our Sun takes over instantly. The entire, colossal structure of the star enters a state of freefall. Millions of billions of tons of matter crash inward toward the center at an unbelievable speed. When all of that falling mass hits the core, the pressure does not just create a normal explosion, it creates a sudden, catastrophic thermonuclear runaway. In a fraction of a second, the crushing weight forces the entire core to burn all of its remaining fuel at the exact same time. It is a nuclear detonation on a scale that defies all human language. In a normal supernova explosion, the core survives. The outer layers are blown away, but the heavy heart of the star collapses down into a black hole. Gravity still wins the final battle. It still gets to keep a trophy. But in a pair-instability explosion, gravity pushes too hard. The resulting detonation is so violently powerful that it actually overpowers the massive gravity of the black hole it was trying to create. The explosion physically unbinds the entire star. It does not leave a black hole. It does not leave a dead core. It does not leave a shadow. It completely, perfectly erases itself from existence. Every single atom of that massive giant, 260 times the weight of our Sun, is violently ripped apart and vaporized into a rapidly expanding cloud of heavy, radioactive iron and screaming plasma. An explosion so bright it outshines entire galaxies, sending shockwaves of absolute destruction ripping through the Tarantula Nebula. It is the ultimate cosmic suicide, an object so powerful and so extreme that the only way for the universe to resolve the paradox is to completely delete it. When astrophysicists first mapped out this inevitable doom, it sent a cold shiver through the scientific community, because this is not just a fascinating story about a distant, dying star. It is a terrifying mirror held up to our own understanding of time and consequence. Consider the raw materials that are created in that final, apocalyptic blast. When this monster obliterates itself, it does not just throw empty fire into the dark. The extreme heat of the explosion actually forges brand new elements. It creates billions of tons of heavy metals, iron, oxygen, silicon. It violently ejects the very building blocks of physical reality out into the deep void. Over millions of years, those heavy, scattered ashes drift through the dark. They cool down. They mix with other clouds of gas, and eventually, gravity pulls them together again to form new, smaller stars. And around those new stars, the heavy metals clump together to form rocks, to form planets, to form worlds just like ours. Every single piece of iron in your blood, every single breath of oxygen in your lungs was forged in the dying, violent screams of a giant star exploding in the dark long before the Earth was ever born. We are quite literally built from the shrapnel of dead monsters. But there is a much darker implication hiding underneath all of this, a consequence that challenges how we perceive our own safety in the universe. We look at our tiny, yellow sun, and we feel a false sense of security. We assume the universe is a calm, stable place because our immediate neighborhood happens to be quiet right now. But the existence of R136A1 proves that the cosmos is a factory that produces extreme, unpredictable violence. The physical laws we rely on to feel safe, the rules that say a star cannot grow too big, or that an explosion cannot completely erase a heavy object, are just local guidelines. They are rules that only apply in the shallow, safe waters of our tiny galactic puddle. Out there in the deep ocean, the universe does whatever it wants, and the most unsettling part of this entire mystery is not just how big the star is, or how violently it will die. It is the terrifying reality of when space is so unfathomably huge that light takes time to travel. The light hitting our telescope mirrors right now, carrying the image of this impossible giant, has been traveling through the freezing, empty dark for 160,000 years, which means we are not looking at the star as it is today. We are watching a ghost. We are looking at a delayed broadcast from deep inside the past. For all we know, the physical strain became too much. The light inside the core might have shattered into matter thousands of years ago. The support pillars might have already vanished. Right now, as you sit here listening to this, the most violent, absolute explosion since the dawn of time might have already happened. The star might have already erased itself from reality, sending a blinding wave of heavy radiation racing across the dark ocean directly toward us. We just have not seen the flash yet. We are living in the quiet, ignorant gap between the pulling of the trigger and the arrival of the bullet. And it makes you wonder if the universe is capable of harboring these kinds of apocalyptic secrets, hiding them right in plain sight behind a wall of twisted time. We spend our entire lives looking up at the night sky, trying to put the universe into neat, understandable little boxes. We write equations on chalkboards. We draw invisible boundaries. We convince ourselves that if we just calculate the weight of the light or measure the speed of the gravity, the terrifying, infinite dark will somehow make sense. We build our entire human civilization on the comforting idea that the physical world has strict, unbreakable rules, and that those rules will permanently keep us safe. But objects like this monster, these impossible giants burning violently out there in the abyss, they do not care about our rules. They do not care about our math. They exist entirely outside of our logic. They are a brutal, glowing reminder that human intuition is incredibly fragile and often completely wrong. We live on a tiny, quiet speck of rock, orbiting a very calm, very average, yellow star. Because our immediate neighborhood is peaceful right now, we have developed a dangerous kind of arrogance. We assume that the entire cosmic ocean acts exactly like our little, shallow tide pool. We assume that the water will always be calm, and the weather will always be clear. But the universe is not a calm place. It is a relentlessly violent, chaotic engine operating on a scale that is completely, fundamentally indifferent to our existence. It is a place where gravity crushes matter into unnatural shapes, where light physically tears worlds apart in a fraction of a second, and where stars grow so monstrously massive that the only way to resolve their existence is for them to violently erase themselves from reality. When we finally manage to peer through the thick cosmic dust and see something that fundamentally shatters the absolute laws of physics, we should not just be scientifically fascinated, we should be profoundly, deeply humbled. It is the universe looking back at us, stripping away our comfort, and reminding us of exactly how small, fragile, and blind we really are. Every single time we build a bigger mirror or launch a better telescope into the cold vacuum of orbit, we do not just find clean, simple answers. We find new, terrifying questions. We discover that the solid walls we thought were holding the universe together are actually just illusions made of shadows. And if the absolute limit of how big a star can grow is an illusion, then we have to accept the terrifying truth. We are floating blind in a dark ocean filled with physical monsters we cannot even begin to predict or understand. The giant star we talked about today might still be burning, fighting an agonizing war against its own gravity, or the structural pillars of light might have already collapsed. It might have detonated in a blinding flash of absolute, universe-altering destruction tens of thousands of years ago. The radiation from its violent death might be racing toward us right now, silently crossing the freezing, infinite void, completely undetectable until the exact moment it washes over us. We have absolutely no way of knowing. We have absolutely no control over the mechanics of the void. All we can do is sit here on our tiny, fragile rock, staring out into the pitch-black silence, waiting for the universe to show us what else it is hiding in the dark.